Welcome to the session on constant acceleration, velocity time graphs. The objectives for this session are to understand and interpret velocity time graphs. The motion of an object can be represented on a velocity time graph. So if we consider the graph on our screen here, with time in seconds on the x-axis and the velocity in meters per second on the y-axis, then this particular velocity time graph represents velocity 0, and it indicates that the object is stationary. Now consider this velocity time graph. Again, we have the time in seconds on the x-axis and the velocity in meters per second on the y-axis, and we have constant velocity, which indicates that there is no change in velocity over time, which implies that the object is moving with constant velocity. And finally, for this graph, again, we have time in seconds on the x-axis, the velocity in meters per second on the y-axis, and we have velocity increasing at a constant rate over time, which implies that the object is moving with constant acceleration. So here's a summary. Here the velocity is 0, and it implies the object is stationary. Here there is no change in velocity over time, and it implies the object is moving with constant velocity. And here the velocity is increasing at a constant rate over time, and it implies that the object is moving with constant acceleration. Acceleration is the rate of change of velocity. The gradient on a velocity time graph represents acceleration, and acceleration equals change in velocity over change in time. So let's take a look at an example. Suppose in a graph, or in this graph, you can see that the change in velocity is 5 meters per second over a change in time of 15 seconds. Therefore, if we apply this to the formula for acceleration, which is change in velocity over change in time, we have that the acceleration is 5 meters per second over 15 seconds, which equals 1/3 meters per second squared. If acceleration is negative, then it is often referred to as deceleration or retardation. The area between a velocity time graph and the horizontal axis represents the distance travelled. For straight line motion with positive velocity, the displacement at time t is represented by the area under the graph up to the point t. Let's take a look at an example. The diagram shows a velocity time graph depicting the journey of a man walking in a straight line. Find the displacement in the first 10 seconds. So let's solve this. The displacement after 10 seconds is given by the area under the graph, as shown here. This is, of course, a trapezium. We can find the area of this trapezium by applying this formula. And plugging in the values, we have that the area is equal to half times 3 plus 6 times 10, which is equal to 45. Now let's have a look at another example. A particle travels in a straight line. It accelerates uniformly from rest to a velocity of 4 meters per second for 2.5 t seconds. The particle next travels at a constant velocity of 4 meters per second for 1.5 t seconds. Finally, it decelerates uniformly to rest in a further 20 seconds. Sketch the graph and find the value of t given that the total displacement is 150 kilometers. So let's begin by producing a sketch. We have the time t on the x-axis and the velocity v on the y-axis. So the first part of the journey, we have that the particle is travelling in a straight line and begins from rest to a velocity of 4 meters per second for 2.5 t seconds. So here's the first part of our journey, O to A. For the next part, the particle travels at a constant velocity of 4 meters per second for 1.5 t seconds, as shown here. And finally, it decelerates uniformly to rest in a further 20 seconds. So 20 is as indicated on the graph, and we join B to C as shown. So let's proceed to find the value of t. The area under the graph is equal to the area of the two triangles plus the area of the rectangle. So here are the areas of the two triangles. And of course the formula for the area for triangle is half base times height. So we have applied that to each of these two triangles. And of course plus the area of the rectangle, which is of course 1.5 t times 4, which is the height of this rectangle. And so tidying up, we have 5t plus 4t plus 6t. And this from the question is equal to 150 kilometers. But of course the area under the graph represents the total displacement. And therefore solving for t gives us t equals 10. And now for example 4. We have the same scenario, but we are required to find the rate of deceleration from B to C. So let's solve this. The acceleration is the gradient of the slope, which is equal to minus 4, which is the displacement, divided by 20, which is the time taken, which equals minus 1 over 5. Therefore, the deceleration is 1 over 5 meters per second squared. This brings us to the end of this session. If you have understood its contents, you should be able to understand and interpret velocity time graphs. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.